What is the Raman effect?
When photons are scattered by an atom or a molecule, most are scattered elastically, meaning that the incident photons and the scattered photons will have the same energy and thus the same frequency. Due to having identical entering and exiting energy, this is called elastic scattering of light, also referred as Rayleigh scattering, and is usually what occurs from scattering of monochromatic light. Two types of Raman scattering are observed, Stokes and anti-Stokes. When the scattered radiation is of a lower frequency than the excitation, it is called Stokes scattering. Scattered radiation of a higher frequency than the source radiation is called anti-Stokes scattering. When the scattering of light is inelastic, what we call Raman scattering is observed. However, this does not occur as often as that of Rayleigh scattering. Stokes-shifted Raman bands involve transitions from lower to higher energy vibrational levels, and therefore, Stokes bands are more intense than anti-Stokes bands, and due to having a higher intensity, are often measured instead of anti-Stokes. However, anti-Stokes Raman scattering also has its uses as fluorescence causes interference with Stokes bands, in which case, anti-Stokes bands are measured instead. The reason why the Stokes lines are more intense than anti-Stokes is because usually, the ground vibrational level is more highly populated than the excited vibrational levels. It should be noted that Raman lines are found on both sides of the Rayleigh lines and that the pattern of shifts on each side is identical. A change in polarizability during molecular vibration is an essential requirement to obtain Raman spectrum of a sample. Coincidentally, Raman scattering due to water is low. This makes water, the universal solvent, an ideal solvent for dissolving samples for analysis through Raman scattering. In general, if the molecule has no symmetry element, as in, it has no symmetry elements other than for E, the elementary symmetry element, all modes will be Raman active. Many number of molecules fall into this category, for example, DNA and a number of proteins. If the molecule does contain symmetry, only the modes of vibrations that belong to the following symmetry classes will be Raman active. In a molecule with a center of inversion symmetry, a vibrational mode may be either IR active or Raman active, but not both.
So how does this spectrometer work? First, it requires a monochromatic excitation source to hit the sample with. This is achieved by a laser. However, different molecules react better with certain wavelengths. For example, inorganic compounds work well with blue or green light. The laser has to pass through a filter before hitting the sample. This helps block unwanted light. A notch filter is usually used because it blocks everything except the laser. It also generates a spectrum where Stokes and anti-Stokes can be measured simultaneously. After interacting with the sample, scattered light is generated. Before hitting the detector, it goes through another filter to remove the laser source. It uses a charge coupling device, which converts a light signal to charge signals. The longer and stronger the light, the higher the charge signal generated. So how would you interpret the spectrum? You can do it the manual way where Raman shifts correspond to functional groups, but generally the spectrum is matched in a database to a molecule. Portable spectrometers can bring the power of the lab to a field setting, however, is less powerful in terms of generating quantitative data. This is usually used for qualitative aspects, to determine whether a molecule is present or not.
We'll now take a look at the real-world applications of Raman spectroscopy. One of the many uses of Raman spectroscopy is for drug analysis. Some of the technique's advantages are aqueous samples can be used. Little sample preparation is often needed, which means dirty or untreated samples can be analyzed directly. It is often a non-destructive technique. It also allows for minimal exposure to unknown compounds, which can be potentially hazardous. And lastly, it's fast and reliable. Another area in which Raman is having a meaningful impact is that in airport security. The current international standard for carry-on liquids is that they must be 100 milliliters or smaller in size. Raman techniques have been developed for which materials inside sealed containers can be identified through the container itself. This technology uses spatially offset Raman spectroscopy. It allows for container signatures to be subtracted from the content signatures. An example of this is seen here. One could theoretically subtract a TNT precursor from polystyrene. This can be used to identify possible explosives or other dangerous compounds without the risk of the operator exposing themselves to these hazards. This technology is likely to become widespread in the future. In 2020, 2 Mars rover missions are scheduled to launch. Each will be dropping a lunar rover onto the red planet. Both rovers will be equipped with Raman instruments. These instruments were chosen due to their remote sensing capabilities and ability to provide important data on the materials and possible life on the planet. This is just another example of how Raman spectroscopy is an extremely versatile technique. There are numerous other applications and special types of Raman spectroscopy. They include detection of counterfeit artwork and ancient collectibles, identification and analysis of nanomaterials, semiconductor research, geological mineral applications, health research, and many, many more. I hope you've enjoyed this brief introduction into Raman spectroscopy.